some of the test development he did is a famous test development. He made a tester in Finisar, which is proudly known as Maya tester, which is on the name of his mother. So he have a wide experience, like a 13-year experience of working in semiconductor industry. So there is too much to talk about, but let's cut it short and let's welcome Pankaj. Pankaj, now you can start the lecture.
Okay, thank you, Yogesh, to introduce me, and thanks, Surya. So I will start presenting directly my slides, and there onwards I will introduce myself. For the sake of everybody know me, hi all, I am Pankaj Kumar Pal. So let me know once you can see my slides. Are you able to see this? I will make it in a presentation mode.
Yeah.
Yeah, now we can see.
So I'm not sure how you are seeing it, but
We're able to see your slide.
We are able to see.
Yeah.
you're able to see my slides, and are you able to see me also?
Yes, yes.
Okay. Okay,
Yeah.
sure.
We are able to see. Please start. Yeah.
Okay, sir. So thank you, everybody. I am pretty grateful that I have got this chance to present the knowledge that I have got in last 13 years plus experience in the industry. So this is my introduction. Basically, I have put a small introduction, bachelor's and master's in electrical engineering from IIT Kharagpur. And I had my career started from CERN, which is basically one of the best labs known for God particles findings in Geneva. Then I moved to Malaysia for some work in Finisar onwards to SanDisk and other further companies, as told by Yogesh earlier. So in today's agenda will be to talk about semiconductor manufacturing processes, that is starting from the sand and till we reach it to the product that is sold outside to the customers. Okay, so first thing we'll talk about is market size and how it's growing and who are the key players. So as all we know, number one market player is TSMC in this field. And while we are talking about TSMC, it is a company which do the foundry job only. What it means, it does the fabrication only for others. So there are two kinds of companies. One is like TSMC, who doesn't have their own product, but they build it for others order. So these are the kind of companies who is not making things for on themselves only, right? So their whole profit, whole manufacturing things are coming from the products that they are making for others, and only from the fabrications. And there are other companies, for example, like Samsung Electronics, or the number two you can see in the right picture here, right? Texas Instruments, and these kind of companies have their own product then that they sell it to others, and then they have their own fabrication also. So those kind of companies, when you see here like 34 billion around for the Intel, it means 34 billions. Most of it is from in form of the whole product or other product lines, while the fabrication part is slightly small. But TSMC, when you see here 55%, it means TSMC is doing only one thing, that is fabrication. So I will play one small video here, which will give you year by year how the industry have grown. So in this place, you can see Intel have been on the top at the earlier like 2007 or even 2008, 10, 15, 16, until that point of time. But you know, Intel have been a key player in at least microprocessors, controllers, and they have been making for PCs, and it was their bread and butter, right? So Intel have been in top until like 2015 or 16. You can see as it moves. And later on, you know, like this was an era of mobile phones, and once it was an era of mobile phones, then Samsung catch up, because Samsung's phones have been one of the top and they have their own fabs, right? So you will see it slowly, like Samsung will be catching up Intel, and then Intel will be fighting back again. Intel will have their own processors for mobile phone. And then you will see like some companies like MediaTek or Qualcomm, who they started building mobile phones, microprocessors, and they grow. You can see, right? For example, in 2013, this is the time when mobile phones were coming into the picture, and until 2023 it had been a booming industry, right? So MediaTek will be keep growing, and then like Intel will be keep going down slowly, and Samsung will be keeping up, right? So this is a war between the titans, you can say, because these companies are very huge. They have like 50, 60 billions of budgets. They are master in their own work, what they do. So you can see Samsung have crossed it in 2017 itself, right? And Intel is pretty lagging behind. Then Intel comes out with their own processors. They try to catch up, but still, you can say SK Hynix is now catching up, right? And then TSMC become third in 2017 or 18. And basically, this Taiwan semiconductor that you see right now in the third red color, this is TSMC, well-known company, number one in terms of fabrications of silicons, and definitely it has 50% plus market share right now in this world. So this is the top company which you can say. And when you see this Intel or Samsung, they are fighting to each other. They have definitely more share towards other places. Other means they have their own other product lines which is giving them this much of money, while TSMC right now you can see 56 billions. That is purely on the manufacturing fabrications of the chips for others. So you might be hearing in this COVID times that there have been a lot of chip shortages, and also TSMC was overloaded for like 5 years of 5 years, kind of like they were building the products for other companies. So this have been a war, kind of a chip war between these companies to get the max share, and definitely TSMC is the master in that. And then Samsung and Intel have their own fabs, and they are manufacturing their own, and even on the top they give the job to TSMC also. You can't say just that they are just relying on themselves. They are building their own, and still they lack. Then they have to go to other vendors. Okay, so other vendors are like Global Foundries also is one of it, SMIC, which you can see here on this color 5%, which is pretty small, but it is also growing. So this field have been growing since last 10 years tremendously. Chips markets have been growing tremendously. Okay, so we will go to fabrication process, how we are building it. So as we know, what we have been doing in this semiconductor industry is making sand and converting it to something meaningful. That is basically inside your mobile phones, inside your laptops, computers, or anything, whatever you see, any kind of electronics, whatever you see around you. It is made out of these chips, and these chips are made out of nothing but sand. So let me just play this video, and that will be pretty give you a feeling of joy how we make this thing. This is a short video to give it a process. So this is what we have. This is our raw material right now, you see. And this raw material is everywhere, right? Like you can find sand everywhere. Sand is pretty in every country or any place you can find it easily. Then to building it to this chip level, it goes through a complex factories and these foundries where we take the sand and then we convert it to these chuckles of silicons right now you are seeing, right? So this will be building from it, and then we will heat it like in a furnace and have a crystal and get like ignite of it, and then this kind of cylindrical metal that you are seeing, that is pure silicon which have to be chopped into wafers later on, and from there onwards we will make these chips. So this video in short, it will show you all. So 100 mm, 150 mm, 200 mm and 300 mm, these have been the size of these wafers normally we use in the industry. And then within this we write the circuit in, and then this becomes a small chips what you see inside like a wafer. And within this there have been many, and now this video like to show you how we chop this into wafers, basically these signals. So this is a basic understanding of the whole fabrication process. But from here you can see that how we have make something from sand until not the chip but the wafer right now. But from here onwards we need to write circuit on it, and then we have to chop it and then test it again and then make chips out of it. So we will go to the next slide. Thanks to SK Siltron, because I get this video from there. So wafer fabrication needs basically sand, and then we have to do the crystal growth, and we have to cut the wafers in, right? So this process is pretty complex. It is not like so easy as it seems. Let me play this video and everybody should watch it, please.
Polysilicon stacking is a process of filling polycrystalline silicon, the raw material silicon wafers for semiconductors, into a quartz crucible. Ingot growing is a process of transforming polycrystalline silicon into monocrystalline silicon, melting polycrystalline silicon into a liquid, and precisely controlling the thermal environment, growing it into a high-quality single crystal ingot. Ingot grinding and ingot cropping are processes in which the ingot surface is trimmed and then cut into blocks to accommodate subsequent machining. Wire sawing is a process that turns ingot blocks into multiple sheets of wafer by vibrating thin steel wires at a high speed to cut the ingots in thin slices. Edge grinding is a process that reduces the risk of breakage due to external impact by rounding the edges of the wafer. Lapping is a process of placing a wafer between a heavy supposition plate and a bottom plate, and then pressing it together with an abrasive and rotating the wafer to flatten it. Etching is a process that dissolves and removes any physical damage on the surface layer of the wafer sustained during manufacturing process using a chemical solution. Double-side grinding is a process that makes the wafer flatter and removes small curves on the wafer surface. RTP is a process that rapidly heats the wafer within a few seconds, which makes the point defects inside the wafer uniform and suppresses metal impurities to prevent abnormal operation of semiconductors. Polishing is the final step for securing the flatness of the wafer through surface precision machining. It simultaneously eliminates microbending of the wafer surface by performing both chemical and mechanical machining using abrasives. Cleaning is a process that increases the cleanliness of the wafer by removing byproducts and airborne particles from previous processes with chemical solutions. Inspection is a process that measures fine details and product quality using a variety of equipment to ensure wafer flatness, shape, and so forth. Particle counting is a process of precisely inspecting the surface of a wafer, measuring the size and number of surface defects by laser scattering. Epi-growing is a process of growing a high-quality silicon monocrystalline film on a polished silicon wafer by chemical vapor deposition. Final product packing protects the product from external shock, dust, and humidity. SK Siltron strives to provide customers with high-quality products. SK Siltron.
Okay, so hopefully the audio was pretty clear to all of you. Can somebody confirm?
Yeah, it is fine. It is fine.
Yeah,
Yeah.
Yeah, sure. So this video, if I speak myself, how many pictures I show, it will not be so much clearer rather than this video. It is a small video, gives you all the process that we take from how we make a proper sand till we have the wafers. And in this video, what you have seen, sand have been converted to a wafer, but wafer doesn't have until any circuits on it. So after wafer fabrications, it goes through multiple of the other things and the circuit writing on it. And there are a few processes followed for it. And I will show you another video for a few more processes or some pictures and some of the slides. So we will go to the next slide. So some important things like clean room environment. It is one of the most important things that we have to have because some of the complexities are there in this whole fabrications because a smallest part of the dust can ruin the whole ignite or whole of the process, whichever whole lot was running into it. So few thousand times more cleaner than a theater of operation theater of a hospital it is. And there are some ISO standards for it that we follow. In case anyone want to go, can go to Wikipedia and read those standards. And the next is photolithography. It is used to pattern circuits designs onto it. Until now, what we see was just a bare wafer, and writing a circuit on it comes with another type of complexity. One of the most used thing is photolithography, where we put some kind of mask of circuit, and it looks pretty complex, but once you see how it is done, it looks very easy, because there is a mask that we make, and that mask can be bigger in size, and then you will take a concave or convex kind of light which will go down towards your to the size of your wafer, and then it will start burning your circuits onto the surface of the wafer. That's how it works. So mask is one of the most important things, and people who work in semiconductor industry, they know there are revisions, versions, hundreds of revisions of the mask, etc., that we go through, and each mask create different kind of circuits. Now, etching and thin film dispositions, these are the process that we follow for removing, writing circuits, and follow on other processes, and ion implantations, that is for basically dopants into wafers, and then thermal processing, that is oxidation and annealing to control the properties of the semiconductor material itself, and polishing process, and then other metrology and inspection, that is basically inspecting if there are any defects or not. And finally, once it's done, we do the packaging, and then at the end we test. This is done, and yeah, I will go through a video to just explain it more so that you can see it and understand. And then when we talk about semiconductors, everybody talk about how much nanometer we are working into, which started from 200, 300, and the last one we know is like 5 nanometers, or even maybe slightly lesser than that in labs. But any product that we have right now, I know of, is 5 nanometers, at least in product base. And these technologies have been bread and butter for many of big companies. They have been embarking, like, I have this 5 nanometer technology with me, and this TSMC comes with an edge for it, like they are going for 5 or 7 nanometers. And then these techniques are not stopping. I mean, I can say it is stopping because there are limitations. Everyone know we can't go below some certain number because of because electronics properties will change of the materials. So we have found other ways to enhance the technology rather than going to the 2D to the 3D that I will show later on. Okay, so I have been in the industry of memory. Memory, basically SSDs or SD card or your pen drive, or basically inside your mobile phone or any kind of electronic device, you have memory. So this have been my industry where I've been working. So a basic product flow is written here right now. Everything start from design, right? So on the papers you design your circuit, then you develop, have like whole team who will come out through a development plan, and then we will fabricate it into fabrication places or those factories. And then probe, when you see this probe is basically testing of those wafers once you have fabricated them. And then assembly means basically we will chop it into pieces, make small chips, and then finally we will do a test that is called final test. And once everything is done, we are going to do the packaging of all that, and final assembly, that is basically last thing to do. So let me just present it in a video which is going to have all this process for a memory. This video is taken from Micron, and you can see the whole flow from start till end.
Memory chip design is the first step in the production of Micron's memory chips. This process involves the use of computer-aided design tools to lay out billions of electronic components that store data on the chip according to the product design specification. During technology development, specific process steps are defined and integrated into a process flow that will build the memory chips. The process steps are tested and refined until the process node is qualified and ramped in manufacturing. Individual memory chips, or die, are built upon pure silicon wafers in a fabrication area, or fab. Fabs are state-of-the-art clean rooms that are 100 times cleaner than a hospital operating room to ensure silicon wafers are protected from ambient contamination. Among the many process areas in a fab, the photolithography area coats wafers with a photoresistant material. Then, like film in a camera, circuit patterns are exposed and excess material is rinsed away. The paths in these circuits are 5,000 times narrower than a human hair. Wafers are moved between different tools and processes using a robotic automated material handling system, or AMHS. Each wafer may be moved through more than 1,000 processes. It takes more than 1 month to make a memory chip. In probe, initial functionality tests are performed on each die on the wafer. A probe card positions probe needles onto each die to send and receive test data. This information is used to generate a map of all the die on each wafer. Only good die that pass all tests in probe will continue through the manufacturing process. In assembly, wafers are first thinned, attached to an adhesive backing, and then diced into individual die using a diamond edge saw. Using the wafer map that was created in probe, individual die are picked from the wafer, then placed on a circuit board. A solid gold wire is used to connect each chip to the circuit board. A molding process encapsulates each die in a protective plastic package and shipped to test. Every memory chip Micron manufactures undergoes hundreds of tests to ensure it meets the highest quality standards. Proprietary Ambix testers subject finished parts to extreme temperatures and conditions to force any weak components to fail before they reach our customers. Additional test equipment verifies that each part meets or exceeds its speed and performance specification. All qualified parts are laser marked with part numbers and other identifying information. Each memory chip is optically scanned to verify strict fit and form specification. Components are placed into industry standard anti-static packaging and placed into boxes for shipment. Many of Micron's finished parts are used to build memory modules and solid-state drives. Automated surface mount assembly equipment is used to mount memory and other components to printed circuit boards. All products are tested using proprietary Micron memory module and SSD test equipment. Finished products are placed into anti-static packaging before boxing for shipment to the customer.
Okay, so this is a basic overall overview of the flow where it have shown you starting till the SSD where we make. This is the whole memory process, and we'll go to the next slide. So in this, one of the most important thing is definitely we know fabrication, and the next comes out to be testing. If you see, there are 3 types of testing if you have paid some attention. One which you heard as probe. So at least in how many forms we have seen the product yet? At least 3 forms if you remember. First is wafers. So wafers is the product itself, because wafers can be directly either sold, or wafers can be asked from some vendor to get, or within a company there can be a separate factory which is sending it to the other factory. So first product you can say is wafer level, and next is component level, which is basically BGA format. Right now you are seeing it can be in other formats also. This is a packaging methodology. For example, BGA is the most preferred. And third one is system level. System is nothing but once you use these small BGAs or components, you will put like 10-20 of them and build a system out of it. Then it comes system level. This is in terms of memory, how it looks like in 3 levels, which I have divided. But if you see any other product, again, it will come to the same way. It will have first the wafers, which have to go through the whole testing flow. Next will be the component, which have to go again from the testing, and the third one, system again testing. And the reason is very simple for these testings, because once you have done the fabrication, you have write your what is the circuits on it. How do you know if the whole wafer plate is fine, it's good? So you have to do some testing, and this is exactly the tester in the picture on the left side. This is called probe, basically. So it will probe it on each of the chip and find out some of the test, which is basically called DC test. In fact, in industry standard, it is DC test, or other names are also on the top of that. Basically, which will find out some parameters of currents and voltages and see which wafer is good, which is not good. On the basis of that, there will be one lot of wafer. So one lot of wafer means one ignite you make. Out of that, you chop, let's say, 20-30 of the wafers. Then each of the wafer have, let's say, 200, 200, 200, then 20. You multiply 4,000 chips you get. So right. So out of it, like each this 20 or 30 wafers, whichever was this from one lot, it all will be tested, and some of them will be good, some of them will be bad. So they have to be tested, and some of them have to be rejected, and some whichever pass will go to the next level of it in the component level. So once those wafers reaches to the component level team or the other factory, which is going to chop it into different dices, and then those dices have to go through the whole list of processes, which I'm not going to show, but it is basically like die attach, and then you have to do some wire bonding, and finally you have to make it as a package, right, which can be used. Actually, the die have the circuit, but it have to make used by someone else, some other product, where it have to have either balls or it have to have pins. So to make that package, next is component level. While you are making a component, you can use one die, you can use 8 die, 16 die, 32 dies, as many dies as you want, or as your product have been designed for. Based on that, once you make a component, right, that component have to be tested again, because you have put like 6, 7, 8, or 12, 13, you know, any as many as dice and some other circuits inside, and you have created a package. You have to test it again, because maybe there are some faults in between, and those defects have to be find out again. So then you have to do the whole test again. At system level, then these components have to put like 10 of them or 6 of them, and some other power circuit and some other circuits you have to put again and build the whole system, and then you test again, like there is none of it is faulty or something. At least these 3 are the biggest level of the testing that we can say. And I think this should be enough, otherwise it will be long talk to go through each of them. But that's how we test a normal semiconductor products: wafer, component, and system. Let's go to the next slide. Yeah, so this is what are the trends we have in the semiconductor manufacturing. As I told before, we all know about this Moore's law, right? Every 2 years there will be twice of the transistors in the same area, right? This have been followed for pretty long, but then we come like the whole industry come up with like how it will sustain, because now the 5 nanometer is the max peak we can get, and if we go below, like if we try to reduce it further, then there will be problems of the interference of within circuitry, right? It's not feasible to make a product less than 5 nanometer, or maybe 1 or some level. I mean, I don't want to debate on that, but definitely there is a certain level which we are reaching already in last 10 years. After furthermore, we can't go down, and we can't make a proper working circuitry. So this Moore's law was based on, mostly it have been on the nodes of the technology. And when we talk about technology node, it comes out to like 200 nanometer, it reduced to like, let's say 50 nanometer, and then 30 nanometer, then 22 nanometer, and then like 10 nanometer, then 8 nanometer. They keep going down, and each node is coming, it's following Moore's law, right? And then it comes out to a time like 5 nanometer, then it's in the industry like how it will follow anymore. So now the strategy have been changed. Previously we have been working on 2Ds. It is like if you talk about 2Ds, it's like your own house, 1-story house, you keep building in one area, and then we come out with more solutions, which is putting it into 3D. 3D is like, I mean, this is a simple idea of many of the people, like, why are we making something like houses? Why don't we just build tall skyscrapers, and which is like 10-story, 20-story, or 100-story, 200-story buildings? And that way, within the same wafer, we will have we will make a lot of it, right? So this have been one example. What you see on the left side, this is called okay. NAND is basically NAND gate, right? On the base of the NAND gates, NAND memory have been built. And here it means that NAND memory basically. Okay, so this 2D NAND memory used to be used earlier, like 6-7 years back or even earlier. I mean, currently we don't use anymore, I think, 2D NAND in no company use. So now we use 3D NAND. 3D NAND is basically you have this 2D and just make it straight up and make many of them on the same area. So within the same area, you will get more of it. So if you remember, like in 2010, I will just talk like one pen drive used to be how much? Just few MBs, right? Like 30 MB. 2010 maybe 1 GB or something. Now you can get like 1 terabyte of the even small SD card. So how we are achieving it? How we are increasing this 1,000 times, even when the Moore's law seems to be not feasible anymore. This is how we are doing it. We are making 2D to 3D transition, and each company have been aggressive about it, have been aggressive of how much tall scrapper you will make and how much I will make. So on the right side, on the top, you can see this proposed 3D NAND structure that is for the individual companies in memory. Right now there is Toshiba. So Toshiba, SanDisk, and Western Digital, these are same, and same is not same. Toshiba, Western Digital have merged with SanDisk, and Toshiba and SanDisk earlier, like not now, 30 years or 20 years back, used to have joint venture for the fabrication. So they are working together with some other company. So it's really complex, but it's same. Okay, Toshiba, Western Digital, SanDisk, all is same when you talk about this technology. So it has PBICS technology, as you can see these 3D buildings, and BICS is basically bit scalable. So that's how the terms comes out to be. Bits scalable. And then Samsung comes out with their own technology, TCAT, and Hynix come out with 3D FG. FG is nothing but floating gate here, 3D is just three-dimensional. Then Micron comes with something, G-Hawk, or their own technology. So each company have tried their own ways to have it transition from 2D to 3D to survive the market, because market is cutting edge and nobody wants this 1 GB of pen drive. Everyone like the cheapest price and most out of it, 1 terabyte I want for like 500 rupees, something like that. The cheapest, right? So there have been cutthroat competition to get on the smallest area, the most dense memory, and the cheapest. This have been the behind story of each company. That's how we have come out to this. And right now, what you see, this NAND technology staging of my mouse should be there, I guess. Cursor. So these layers, when you see the 64 layer, 2017 BICS3. So basically SanDisk or Western Digital have been giving it a name of BICS, and every memory node comes out like BICS 3, 4, 5, 6, 7, 8. I think 7 is not there. Or anyway, I won't tell anything deep inside because many things can be not spoken. But there have been a fight to get more and more and more layers. It's like how much layers you can make. How many stories of the building you can make, that much of the memory you can fill in. That's how it have been growing. And right now 260 something layers at least SanDisk is making, and some other companies are making even further more stories. So where it started from 2017, 64 layers. So I mean, just will give you a very small idea what is this layers. Hopefully you can see my mouse cursor properly. Let me just get it into pointer mode. Fine. Okay, so when you see this green color plate, right, or you can see this green color here, some of you who know about memory, any kind of memory, all have these word lines, bit lines. I hope you all know. So this all are like word lines, this green color, and whatever you see, this horizontal, what is this color, like not even red. So this color, this line is bit lines. These are nothing but metals actually, and these are connecting on the bottom this 2D structure of the silicon, and each of it getting connected to individual transistors, which is single bit cell of the memory. Now what's done is basically on this 3D, when you see this thing remains similar here. This is bit lines again, and the green color what you are seeing here becomes no more like a stick. It become like a plate, right? So you can see like 4 of them, 4 sticks, right? And there are 3 sticks. Now these 4 sticks have become like 4 plates basically. And then whatever you were seeing here on the bottom, which was basically a base to make a transistor, have become on this this yellow color kind of cylinder which is going through the holes, right? If you can get this picture clear, can you see this line which I am just putting my pointer through? This is nothing but a circular rod, basically yellow color circular rod, which have been put into these holes from the top to bottom, and this individual connection between this green color versus this rod, that is individual memory cell now. And this yellow color stick which you see, it is the silicon basically, and have everything inside to make it a memory, which it was doing in 3D. This is how we do it in sorry, here in the 2D. The same thing is done in 3D now in this way. So this 2D to 3D transition was not easy, have never been easy for anybody. And making bigger and bigger and taller buildings is not easy, because whenever we do any this kind of applications, even 2D also had a lot of issues at starting. You keep fixing, then 3D comes out into the picture, then again need to fix a lot of issues, because this pillar which looks like so straight, and you put this yellow color straight down into this hole, it is not that easy. It is not even have the same radius across, and it is not so easy. It can flip, it can fold, it can do a lot of problems can occur during this stuff. This is a state of an art thing to make this kind of things, and a lot of complexity have been come across, and individual companies have been handling it in a different way. And this is basically 260, I guess, layers of the last technology which SanDisk have. This number is not shared, so I'm not going to tell it. Even 260 something is in 2023 right now. So big six have been already there, and some other technology which will be coming will be 200 something. So just consider it like a 200 story of a building. So making 60-story building versus 200-story building, definitely 200 will be difficult. And this is how the new trend is going. And definitely there will be a time once these stories will have like, now, okay, after this we can't sustain. And sustain is not just because like how many stories you can make. It is like you can make stories, but will it be viable with the cost, and will it be viable with the technologies, and will it be with the less defects? So everything have to be counted, and then only we will have the technology driven towards somewhere. And now I think this 3D NAND have developed past 10 years, I will say, a lot. And right now we are in 200 plus layers in every company is almost there. So next thing, challenges this have to go through definitely, because semiconductor industry have a lot of challenges. One of it is shrinking process technology. Definitely we want as many as transistors inside a small area. Our processors also, when we started this Pentium or Pentium different versions, and then even memory, anywhere, any kind of manufacturing facility of this semiconductor, any device always have high demand for, I want it on a least area, the max transistors, or the most efficient one, the least power consumption, and everything have to be like great about it, right? And then the area have to be very small. So this is called shrinking process technology. The least you can go is 5 nanometer, it's already there. And then you can go 3D, it's already working on there. Some industries are easy to adopt this 3D, some industries, a lot of problems they are facing, but still we are going in that direction. Next is yield improvement. Why it is so important? Because the point number 2 is yield improvement for a reason, because maybe if anybody can guess, what is the first yield of the first wafer we get? Anybody want to type anything? I can read any typing. Any message? No message.
1%.
Okay, you guys answer 1. Anybody else want to answer anything?
0.5%.
Okay, fine. Yeah, it's okay. So first yield goes 0%. So how it goes, first, whenever we make the first product, it never pass any of the test. And from there we start, okay, these are the changes we need to make into the next version, and then mask changes will be there, or some design changes will be there, some new flaw will be there. So whenever there is a new technology we are growing, we will have this yield number to be 0, and from there onwards we have to bring it to a big number that have to be like 90 or something. And we don't have long time, because the next technology is coming within next 1 or 2 years. Otherwise the competitor will go into another 50 layers, he will increase. The competition has been very tough. This is how the silicon industry or semiconductor industry is. Basically they have been in a cutthroat competition. If you don't make another story, I mean, another building up, the next competitor will grow another 10. So time is less, Your production have to be also there. It have to be viable in the lower price. Your customer have to be satisfied. It have to go like multiple years, and you can't just make any wafer and give any product and then sell it to someone, and the next day he will come, oh, my pen drive is not working. Then your company is gone. So in that case, yield have to be like best, like 90 within 1 year or 2 year, once your maturity on your technology comes. So any technology, like right now whatever you are buying, maybe products, it's not made just last year. The technology was made maybe 3-4 years back, and it have got the maturity now. But right now the technology that the company is working, maybe it will come next 3-4 years, I mean 3-4 years later. So that's how it is going. And then every company have cut throat company to bring their technology as soon as possible. So this is how it's going. Yield improvement is one of the biggest challenge for every company, because yield always drop, and your whole program, your whole whatever design you have done can go to, can be dusted, because you are not able to get your yields or whatever you thought, like, oh, I will make 300 story. Well, you can't even make it in the next 4 years. Then no point of making it, right? This happens actually. It really happens. Many companies have like haven't considered their even plan. I mean, they consider for 1 year, then they stopped it. They say like, okay, we'll sell the old thing, whatever we had. Like this kind of things have happened. A lot of money goes in R&D and those projects also. Okay, next is cost control. I think I have mentioned this word many times. Cost is very important, because again, customer don't want to spend a single money. They want to go least possible, and there are multiple players in the market in semiconductor right now. And then comes out like TSMC kind of companies. They will make things on very cheaper price for you, and then if you try your own fab, it won't be viable even into the market if they put. So cost have to be keep in control, because manufacturing is not cheap. Even one single tester you buy, it's millions of dollars. I have gone through, while just now Yogesh was mentioning, I have made some tester. Built some tester, because the tester that our company was trying to buy for some other company, it was coming for millions of dollars. And then we make our ingrown, house-grown testers. It can save a lot of money, like millions of dollars. So cost controlling is one of the biggest thing, and there are mostly you will see companies, half of the projects are on the cost-cutting projects. Okay, so next is materials and supply chain. So it is one of the most important, because you see, like, this manufacturing is not happening at just one place. It's not happening like if we have a plant in India, it is just in India and we are selling in India. It is everywhere, right? Your wafers are coming from one country or one part of the globe. Then once wafer is done, then to convert it into component, it's going to some other country in some other place. Then from that small BGAs, if you want to make the product, it is going to another country. So I mean, even though you are one company, but your company nowadays in MNC environment, it is everywhere. So this supply chain becomes pretty important for your own consumption, your own things. And then selling your thing is another. Supply chain problems are really very high, and people try to keep their things at the nearby or the possible, so that you don't have to go multiple send one place or the other. It's very costly, because the packaging is very costly, and moving things are pretty costly in terms of wafers if you are sending. So materials and supply chain is key factor, and the last one is environment, regulatory concerns, and then I will add another one, which will be geopolitical, which comes in last 4 years. So environmental, definitely government have their own concerns, like you can't do a lot of pollution or lot of these greenhouse gas, etc. These kind of things are there, and they have to take care of this sustainable practices. So if you want to have sustainable practices, you have to go through a lot of rules and regulations. At the same time, this geopolitical war situations, I will say, they also cause a lot of mass problems for the companies. For example, like Huawei case, and this China can't get sufficient chips, and USA putting some kind of restrictions and putting a lot of curbs on these chips selling from one place to other, technology transfer even. So this plays a lot of role. I mean, it is all a big system. Now it have its own ecosystem, which is running by itself. Some countries have monopolies, some companies have monopolies, and that's how it's going. So it is whole, I think, give a overall picture of the challenges right now, how the semiconductor manufacturing is suffering, right? So let's go to the next slide. Oops, sorry. Yeah. Okay, so next, these are the last two slides that I have. Mm. So how about like as a student, what are the things that you can have to go into this industry? So basically, I mean, education definitely have to be one of the key role. You have to have the right degree. You have to be involved into the right university or college and have proper at least sufficient numbers to, or your CG or whatever it is, to get into a company. Next will be technical skills. Definitely you have to grow your skills into electronic circuitries, semiconductor technologies, and there are a lot of simulation softwares like Palladium or others. Like there are many of them, right? It is not just one thing. It is development, then it is out of the mass design. A lot of jobs. It is vivid. So you have to have those kind of technical skills before you enter from your college. The next will be if you have some experience in that field or you have your internship done in that any place, it will be helpful if you go to the next place. And then projects, if you have in semiconductor related kind of projects or electronics related, that will be helpful. And then these are secondary, I will say, because soft skills, industry knowledge, if you have, it's good. If you don't, because all students can't have it. And then cultural fit, these are the things which are definitely checked by HRs or many interviewers, right? Like I will give you one example of we won't take any names. So there was one company which don't hire from IITs. Then I asked directly, like, why you don't hire from IITs directly? Then they say, like, IIT people come and then immediately within 1 or 2 years they leave. It doesn't seem like they are gonna stay much, so they don't hire. So this can be, and cultural fitting, and the person had the passion to work into semiconductor, and these kind of things also matter sometimes. Also, it can be a judgment based on that. And then problem solving, this is, I think, every job needs it, so it's there. So these are the things required. I think hopefully all of you will have it. And it comes to the conclusion point. So the conclusion of the semiconductor is the semiconductor industry have been pretty long. It is not today's work, right? It is since 50s or 60s, since Moore was in have given this law of Moore's law, and then since 20, 30 years, 40 years, it have been growing rapidly. And last 10 years have been even amazing. And there have been like chip wars, there have been lack of the chip, and a lot of things have been, and then there have been downfall also. So this industry have gone through a lot of ups and downs. Mostly it have been a booming industry, and in coming future also we see a lot of things coming to the, at least if in perspective of India will definitely have a lot of things coming to the semiconductor, because we have this plan from the current government which shows a lot of interest in semiconductors, and we know that there is no proper wafer fab in India, and it seems right now the government at least want it, right? Only like Japan, Taiwan, US, some places, or some countries have it. I mean, these kind of countries have the wafer fabs. Very few places have, and wafer fab is a very huge investment. So it have to be at a country or government level, have to support it. And not only that, it have to come through a lot of technical challenges. Even like China want to have the cutthroat competition in that, but not able to get it, right? So a lot of ups and downs is there, a lot of geopolitics is there, but India at least seems to have a good future in these terms. So this will be it. And if anybody have any questions, floor is open.
Yeah, thank you, Pankaj, for a nice presentation. Now the seminar is open for questions. Yeah, Jyoti, you have some questions?
Hi Pankaj, I'm Jyoti. I'm a faculty member here.
Hi,
So
Jyoti.
I know to initiate this discussion, I thought of asking you first so that student get temptation to ask you more. So you had a very nice presentation and very nice overview. I understand time is short. So maybe in the future you can give a very detailed presentation on some key aspect of problems. Maybe that will be useful for people. Just have a like a very simple question what you heard, 2D NAND versus 3D NAND. Okay, you have given an analogy with an high rising building. Okay, so I'm asking as a student. Okay, please keep that in mind. So in a childhood we have seen single story houses majority time, right? Maybe a school building, second floor, maximum first floor, maybe if you're lucky. Now this is usual that you see a 20-30 floor building next to you wherever you go, isn't it? So now the constructions are different, the availability, instrumentations are different, the tools that were used different, cement different, the bricks different, everything is different nowadays. Okay. So the question is, if you look at the high-rise buildings, the price that you pay for the upper floors are different than the ground floors. Okay, and same the services that you get into the upper floors and lower floors are different. Now, if you compare this one to the semiconductor technologies, right? Do you also think of there is an high price things that kept on the top floor as compared to the middle floor or lower floor?
Okay, yeah, pretty relatable question you have, Mr. Mohanty.
Mhm.
So surely it is, no doubt or undoubtedly, when you are making this kind of technology which have like 200 floors, or let's say when I say this, like these are the plates, right? These are the metal plates which are basically word lines, and if your memory cell is this kind of pillar which is coming from top to the bottom, you are going through. So I haven't put a real picture of it. Basically how it goes is it goes like slightly like this, keep increasing, then go down, then keep increasing like this. Like it is a different shape actually. It's not a simple kind of like cylindrical shape. Rather it keep going up and then down, then up and down, and like 2 times fabrication it's make. There are some kind of these kind of things are there. And then definitely making, I mean, like lower side of it will have more like issues, and upper side will be better. These kind of things are also there. So some of the like top floors are better, bottom is not. These kind of things is there. So mostly what happens, like whenever testing persons, like I mean someone who build it, I mean, definitely he have to go through all of it, like how he will design it in a way that this kind of things can properly go through this 200 plates. So when I say this 200 story means, just consider there are 200 plates. These are like floors, right? Each floor is one word line. Okay, this is basically a metal plate. You can consider 200 metal plates, and then they have holes, and then you are putting one like pillar in it, and that pillar is basically silicon make of this material which makes a like memory cell, right? So some places it's thin, some places it's thick, and then some places it's bending, right? So based on that, some of the plates, overall every cell have better chances of reading the right memory, I mean right thing, 1 or 0. Some of them will not have, some of them will fail, some of them will like pass easily. So then we have to have mechanism also. We have to pay back mechanism later on in the firmwares or somewhere to fix the things there, right? Because when I mean, we always have errors. We always have errors in reading memories. Like let's say you have your 64 cells in a row, right? 64 bits. Then you have some kind of error. You will do correction. So your firmware will handle it later on. Let's say this particular layer which is in the middle, it has like more issues than this basically middle layer have to go through more correction error. This will take more time while you are reading and writing. That kind of things are really there actually. So each floor have, I mean, top floors have a slightly more benefit. And as you go down, you can see one more thing. On the top you have bit lines, right? So they have first access, they are fast. At the bottom it's not that fast, and then there are problems also keep growing as you go down.
So, Pankaj, how about if you have a bit line in between?
Right now, bit line in between, I have not seen. Mostly they make, I mean, there are multiple designs actually. So bit line in between, it's slightly kind of, I have not seen until today. The reason I think is because they are big metals So, like how we design bit lines are basically work as a capacitor, right? Because when we do this charge sensing to read as a 1 or 0, I mean, any cell, does it have a 0 or 1? When we read that, we use the capacitance of these bit lines, right? I mean, if you read this, you will know this. So they have to be slightly big. They can't be very small or something in the size. So they are big metallic rods kind of thing. So it takes a lot of size actually. So right now you see these sizes are not real actually. So this is to just give a demonstration. But once you see, maybe here you can see this, right? This one, this also doesn't give proper sizing. But you see this red color here. They are big. If you consider to this green color, this structure, they are big, and this is made in just in one shot. This, I mean, these 6 plates, they are made in one process, and these bit lines, they are metallic layers put separately, and they are huge in size. They will be like more than half of it. It looks small, but in reality, it is more than half of it. So you can't put another one somewhere in between. So it will not be feasible in that way. Some of the design maybe there, in that case they are doing it in different, but mostly if you see like this one, 162 layers, right? Whole of the circuitry, what you see at the bottom, okay, my finger you can see, but this cursor you see, right? So whatever you see at the bottom, this all is a other circuitry, and this on the top which you see, it is pretty big than what you see this blue color in the size actually. So it is not in between actually, it is at the top only normally.
Okay. Thank you, Pankaj.
Yeah, I have one question. Why you restricted to 260 layers? Can it not be 500, 1000, 2000 layers?
Yes. So why the same thing, Surya. So the thing is, when we grow the layers, right? Your rod length have to be more. There is a rod that we put. You can see these yellow color rods, right? They have to go through, and the whole structure have to sustain. So it is similar
Otherwise
to
it
the
will bend. Okay.
yeah. The thing is, as we increase the layers, we have physical problems will be caused. Physical means like it will either get tilted, or like some two layers are touching each other, two word line shortage. So once we started having this kind of like first bigs of the 30-40 layers, they have some like two layers are just like this touching each other, some of them getting flipped all together. More problems will come. So as soon as we keep resolving the old problems, we increasing slowly, and until we have a situation we can't go any further. So we have reached to a, I will say, we started with like few layers only. Today we have 200 layers. It's a big achievement. Okay. It can go maybe 500 also someday.
Yeah.
So it's not a fundamental problem, it's a process. It's a process.
Yes, exactly, Yogesh, you are right. It's not a fundamental problem, it is a process problem.
Okay. So now we have few questions from students. Narendra, please go ahead.
Sir, my question is, will there be any delay from the top metal layer to the lower metal layer? Hello, sir.
Yeah, got it. There will be slightly, but it is not going to affect anything actually. It is there may be actually, there can be, because there is some like, how to say, there is a distance is there, but it will not be, it will not cause any issues actually. Mostly it is pretty far from there.
Okay, like when we go for a higher, like more number of layers, the complexity of making that layers will be complicated, or reducing the size of the nodes will be complicated. Like, which one will be the most complicated thing for us?
Couldn't get it. Say again. Which one will be which things you are comparing?
The one is like we are building more of layers, metal layers, like apparent. Like if we go for guess 500 or something, that will be complicated. Are the nodes, we are reducing the size of the nodes from 3 nanometers, 2 nanometers.
Okay, yeah. Okay, got it. So in today's situation, okay. By the way, who was asking this? Narendra, right?
Yes.
Yeah, Narendra. So Narendra, the thing is now, not even now, like 6-7 years back, we are already in a situation. We have gone as low as possible in terms of nanometers, like 5. Below it, it's maybe it's in kind of labs working and all, but in manufacturing processes, they have gone like 5. Even TSMC, which have been master of all this thing, they also giving options for 5 nanometer. But 5 nanometer chips are getting a lot of problems also. Be sure about it also, because the product have to be working also. But this 3D structures have been, once we reach there. So now going down on the 2, 1, or even like you say less than that, or angstrom level, or going to the electron level, will be pretty tough from here onwards. Rather, making the buildings was the cheaper, viable, and easier option.
Okay, thanks. Thanks. So that's our question.
Sure, sure.
Okay, now after, please go ahead with your question.
Yeah, sure, sir. First of all, thank you, Surya sir, for organizing this industry lecture. And thank you, Pankaj sir. It was a wonderful talk. Actually, I'm a final year MTech student of semiconductor materials and devices. And sir, actually, our branch is more focused on the semiconductor device manufacturing.
Yeah, please go ahead with your question. Please go ahead with your question.
Yeah, sir. It's more like a discussion, sir. Actually, just wanted to discuss, because we have our placement season going on, sir. Actually, the placement season is underway, so I just wanted to discuss about these some placements. So our branch has it's more like focused on the device manufacturing. We have students working on memories and transistors. So students are working on resistive random access memories and flexible transistors, and also these 3D architectures. And we are also working on synthesis of 2D materials like graphene.
Okay.
So it would be very good. It would be a very wonderful opportunity for us if you have any job opportunities related to our branch. So Pankaj sir, I would request you to please drop your LinkedIn as well, so that we can have more elaborative discussion there.
Okay,
Thank
sure.
you,
Yeah. Yeah. So how to say your name? Soed Akhtar, right?
Saud, sir. SAUD. Saud.
Saud Akhtar. Okay. Yeah. Saud.
Yeah.
Okay. Just I don't want to. I mean, this year you are passing out or next year?
2024. 2024. I'm a final year, so 24. Yeah.
24. Okay, got it. Yeah. So one thing everybody might be aware right now, this industry is on the downturn, right? Are you aware of that? Or not
Yes,
aware?
sir, somewhat. Yes, sir, somewhat we know.
So
Market
be
is a little
aware.
bit down. Yeah.
Be aware. Many companies, including Western Digital and even some big names, they don't have openings. They have cost cutting ongoing. They have layoffs ongoing, and I don't want to put anything, but I will just say one thing: go through news, read about the industry news, read about more by yourself. But right now, the industry is going pretty low. At least Western Digital, I know of, they are not hiring. But if internships or something is ongoing, try on the page of the website of the company, Western Digital.
Yeah.
Then go to opportunities and look there. Okay.
Yeah, sure. Sure, sir. Sure. Thank you, sir.
Yeah.
By the way, I think Intel is still hiring. Intel, Qualcomm, and I heard of Google have started new functions in India, and then Amazon also. Try there.
Yeah, sure, sir.
Yeah. So Sri Chen, do you have any question? Sri Chen.
Namaste, sir. Sir, my question is there any limitation like Moore's law in building the number of floors in 3D structures? Sir? And if there is, if as you keep on increasing the number of floors, there will be mechanical effects and thermal effects in the circuit that mainly affects the ground floors. How can we treat that, sir? If there and if there are those effects are considered, then the efficiency of the circuit may decrease. How do we treat those effects?
Yeah. So hi, Sichan. Namaste to you. So basically, heat. Yeah, you are right. Heat will be at certain places will be more, certain places will be less. But we have some kind of feedbacks also in the system. I mean, when the heat heat is there and some kind of property change for it, right? We have some circuitry which will give the feedback as per the temperature, and there are some temperature sensors inside BGA. So this is taken care actually.
Sir, is there any limitations for the number of loads to be built on in 3D?
Number of what?
Number of floors. I mean, you said 200. Like, if we consider it as a
Yeah.
building.
Yes. So see, the thing is, at first, if you see this chart, the slide that I had, sorry, the slide, this side, if you see 17, we had 64 layers, right? 19, we have 96. In 2 years, we changed 64 to 93, around 30% more, right? Then we add another, how to say this, 15% more. I mean, 30, we keep adding. The next year, next 2 years, we add another 50 layers. In the next year, we add another 70, 80 layers. So the design guys actually add layers, and adding layers comes with one more thing actually. If you see, what is this layer? Layer is a word line, right? Word line is a page, right? So page, on memory, we have pages. I mean, memory you read, then you will know there are some pages, right? Word line, bit line,
Yes.
word line makes one page. So this what you see here is a one page. So how many layers you will have, that will define how many pages you will have. So now the thing is we keep growing, but then the designer person think of like, should I put 162s or I should put 163? Because he will come out with a whole memory count. Like I am planning for like this much space. I am planning 1 terabyte memory. Then he will come out like, okay, if I put 163 layer, then I will have 164, this many pages I will have. If I have this many bit lines, it will do some calculation. Then these numbers will come out in that way. Somebody will calculate. But extreme number cannot be. I mean, what can be like, let's say the next technology persons are talking to this fab guy, asking like, okay, what do you think? How many layers I can cause? Just try 2030. Then he will say, okay, 2030, then I will give you 25. And someone will calculate, okay, 25 is okay. This way, the fab guy will start thinking of his process changes, think of his last year, what was the problems he faced when he make like, let's say, 112 layer, we have 2020. Then he was very confident. He say, you add 50, we didn't have this technology go very well. You add 50, we will be able to make it. Then add 50, like 160 got problem, or then got better, good. Based on that, he will say, okay, we can add another 100 this year. This way it is keep growing. It is not, it can't be certain. It can be only based on the previous learnings. How the last technology go, what are the things that we faced in the last technology on base of that.
Sir, another question, sir. If we keep on increasing the number of layers, how can the ground layer upon which we build the other layers provide the sufficient mechanical strength so that the circuit is withstands the circuit can have stability?
Correct. So there is one more thing you need to see. While we make this, like, let's say this 2022 model, which is 162, and let's say this big next layer 200 something, the layer to layer distances, right? They also change. So let's say you have this pillar, let's say this long, and then you have fit in this many layers. The next one you make little bigger and put more. But when you reduce the distance between two layers, then you have other kind of problems. But when you make it near by near, and you have holes and you have drilled something through it, and those holes have put like multiple of the rods, then it will be sufficient hard, right? Just consider many layers and put many pillars in it, like 100 pillars. 100, I mean, these layers have holes. These layers have holes. I haven't given the top view, but you can see on this 3D NAND structure here that they have holes. A very good view is here. You can see this, right? This green color is here, right? Then the top to bottom, this pillar is coming. There is not one pillar. There are like hundreds of pillars. One block will have like 100 pillars. 100 pillars going through 100 of the layers will give sufficiently firmness to the structure, right?
Okay, sir. Thank you.
Yeah, sure.
Any more questions from the students?
Nobody asked about this why slowdown happened, why there was a lot of demand. Because that was a common question everybody have. Normally people ask.
Yeah, I think once government of India starts the semiconducting machine, again the boom will come, hopefully.
Yeah, yeah, yes, definitely.
Yeah.
Just wanted to give a point of view to everyone what's going on right now in the industry, current trend in the industry. So in 2021, 22, or even 20, it was pretty booming because everybody know that a lot of chip shortage was there. You can't get your cars because car people will say we are not getting chips, and there were a lot of articles. There are chip war is ongoing, chip shortage is there, right? Lot of articles were there around 20 to 21 or 22. But then suddenly 2022, end of the 2022 and 23 this year have been pretty slow for this industry, and the reason being that during the, I mean, some people know then good. Otherwise, for the information of all keeping in the one page, in 2020, 21, 22, in the COVID time, everybody was using lot of hardwares, lot of video calls, lot of all these created lot of memory requirement and lot of computer, laptops, and mobile phone. Everybody needed it suddenly. So a lot of growth comes immediately for this industry. So 2020, 2021, at least until the COVID things pretty go down, there was huge demand. And how the companies works on the base on demand, there is a whole team which will come out with their plan for the future. So in the 2 years of trend, they saw a lot of huge demand. Based on that, they extrapolated and say, oh, next 2 years are going to be pretty high. So what they did in 2020 till 2022, they make demand like 5 times, 10 times, and they build lot of items prepared. But then suddenly this COVID go away, and then demand also like go like a balloon, and then low demand suddenly after 2022 mid somewhere demand goes very low, and almost all companies have lot of inventories. They have built lot of material based on their own teams suggestions and extrapolation, and they have done it totally wrong. They didn't consider the fact that COVID is the thing which is creating a like kind of bubble, rather than considering a long term kind of sustainable high demand. And then 2022 mid onwards, suddenly all company faced it. They had a lot of all semiconductor companies are going through it, actually most of it.
So how
So
long
they,
this will be? How long this will, maybe for 1 more year or 2 more years?
yeah, so at least last 5 6 quarters I have seen which all companies are going pretty bad situation right now, and next 3 quarter 4 quarter can be affected.
Okay.
Yeah.
So any
Okay.
more questions from the students? Okay, so as you suggested, students can go to the company's website for the internship, and they can apply over there if they
Yeah, yeah,
if they
please
advertise.
go through, and definitely the top companies which I show you in the starting of the slide.
Hmm.
Go through all companies website.
Okay.
They are the top companies.
Okay. Okay. So suppose if students have any questions, can they ask directly to you, or how it is possible? Like, can they contact you, or
I was not able to hear you, Surya. I think your voice.
suppose if students have some questions, technical questions or anything,
Yeah,
can
please
they,
contact me.
okay, can
You
they
can.
email you? Can they email you?
Yeah, they can directly ping me in LinkedIn. No problem. My name, I think easily can find. Just write Pankaj Kumar Pal, IIT Kharagpur. You will get it.
Okay. Okay. Yeah. So if there are no more questions, let's thank the speaker, Mr. Pankaj, for his wonderful lecture. And I think his insights will be very much useful for all of us in terms of technology development, particularly the transition from 2D NAND to 3D NAND, which is wonderful. And then he also discussed more about the insights of 3D NAND, like what are the limits and then what is its capability. So thank you once again, Mr. Pankaj, for your wonderful lecture. Yeah.
Thank you.
Yeah.
Thank you, Surya.
Thank you. So Yogesh, would you like to say something?
Yeah, thank you, Pankaj, for inspiring our students. We'll be in touch,
Yeah.
and
Yeah.
students can
Thanks.
be in touch with him.
Yeah.
Yeah.
Thank
Thanks,
you.
Yogesh, for giving this opportunity, and
Thank you.
thank you.
See you. Yeah. see you sometime after some time, maybe next year or so sometime, or even before that.
Sure,
Thank
sure,
you.
Mr.
Yeah.
Yeah, no.
I'm closing the session.
Yeah, sure. Bye, everyone.
Bye.